thanks a lot for the revision. So when I realized that the time is 1 hour, half an hour, I thought that I will be alone with the using the board. But they see that I am not the first one who is doing that. So, but I will try to fit in the time. It's suggested. Okay, so I want to advertise. So let me also the name in the contractads, which comes out in the contraction as operas. So this is some theory that generalizes the notion of the operas, and this is all the joint work with my student Denis Liskov. And most of the papers are published by his name, but there's also a couple of joint papers on the one so far. Yeah, and the story is about. So the story begins from the following question, which I'm mostly discussing today, because this is the question about the configuration spaces on X. So for me, X will be a manifold. It's not necessary for the definition, but for the applications, it's quite important for historical physics. And also, what I mean by configuration spaces, meaning that I'm considering the manifold X, the d-dimensional manifold X, and I'm considering the collection of points P1 up to Bn, so that points are indexed. So it's the order configuration space. Order configuration space. So practically, what does it mean? So that means that I'm considering x1 up to xn such that the word configuration means that, so first of all, xi belongs to x, and second, for any I not equal to j, xi is different from z. So they should not collide. This is the story when we're speaking about the configuration spaces. But of course, it's not quite useful to have the points which are different one from each other if you want to describe the geometry. So, but let me rephrase this story in a bit more fancy way. So I'm saying that this is xn without the delta, where delta is the set of diagonals in S. So delta is just the union of index by pairs, xi equals xj. So this is just the main object of my study so far, but even not this object is the main story, but let me start to do some classical theory, because if you, so nowadays when you're looking for the configuration spaces, so first of all, this is not a compact space. This is you throw away something closed, which is already not relevant for the story. When you try to do what do people want to do, people want to compute the integrals over these points going through the on a manifold. And second, what is also important is that it's not really relevant to look for one specific n. It's much more useful to look for the whole n together. So for the union of those configuration spaces. When you look on the union of configuration spaces and you want to find some algebraic structure behind it.
Just the disjoint union, right?
Yeah, just joint union of n, but so the key point, the key idea of the opera theory is that you have to vary your index n, so you have to consider all n at the same time. Why it's relevant? So the one way of explaining it is the following. So instead of thinking about the points, so the main geometry happens when the points going closer to each other. So when they far from each other, this is just given by the geometry of x. But then the question is what happens when they're going close to each other? When you can think about points going closer to each other, or you can do the other way around. So you can say, so let's, instead of thinking about the point, think about small disks. around those points. So homotopically it's absolutely the same, so you can contract everything. But then if you have the small disks, or even not so small disks, so you can do bigger, so then you can, instead of one disk, so you can put inside this disk another collection of points. And what type of operations this gives me? So instead of thinking about conv n, so let me consider conv tilde n of x. So this will be the union small balls d1 dn such that di does not intersect with equals empty set, so they do not intersect. And then on this union, you have a nice operation, so you can substitute one ball into another one. So that means that you have a natural operation conv n of x, and then conv m, but not of x, but of rm, rd. So the balls, so what is given here? So if I'm looking for the balls inside the in the flat space, in not so here there's only local story. So then there's a map to the conv m tilde of x, and here n plus m minus 1, right? So if I have 1 up to n points on x, here 1 up to m points inside, so one of the points was replaced by m points, so n plus m minus 1.
So, you said that if you take this, isn't it the same as taking points with the tangent realization of the?
Yes, you're right. I'm sweeping under the carpet. You're right. So to be honest, so if I want to do this formally, so you have to, so this construction works well, works nice. If there exists a framing, as it was discussed previously. So if you have the framing, so you know what is the north, so you have some vector field, and you know where is the north, and then you can place, and then here you consider the balls which are with the standard trivialization of the tangent balance, then you can put it one aside to another. So if you do not have framing, then there is the way how to increase the story. And I will say in a moment how to do it with that. So in this case, you instead of configuration points, you have to think about configuration points plus the tangent vector, and then you can do the same story. But this story is much more complicated compared to the tangent vector. So what you get out of this picture is that, so this is the main example of the little disks operand. So the little disks operand is the following thing, is this precisely ed of n is the configurations of one ball with n 1, 1, 2, with n balls inside it. So this is my space, this conv tilde n of rd, and then you have what? So you have the map here, and then also you have, so if you substitute instead of xr, so you see that you have the same map for one rd. So you have, what does it mean? That you have the map from ed of n times, so times ed of m, ed of n plus m minus 1, and this collection of maps are indexed by I, which corresponds to the I going from 1 up to n, in which input you are substituting the second piece. And the K property of this story, so these operations relations are associative. So this is what people call the opera theory. So the formal definition, let me give it here. The opera in category C consists of the data of the collection of objects P of n and collection of maps P of n plus m to P of m to P of n plus m minus 1, which is associative and equivalent with respect to renumbering of the elements there. So ED is one of the main examples of the operands, and each configuration space, conf n of x, the union of those n, is a right module over this little disk over ED. Little disks opera. So this was the classical theory, and now what I want to give you one suggestion, and this is the key point of my talk for today, is to suggest you a kind of generalization of this story, which will be the following theme. So now let me allow to consider a bit more general configuration spaces. So let me consider the configuration spaces such that I allow the points, I'm allowing the points to collide. So I'm saying that some points may collide and some points may not collide. So what does it mean that some points may collide and some points may not collide? So I want to add the property I want to fix this rule. So in order to fix this rule, so what does it mean? So I have to fix the graph gamma. So I say that I have points 1, 2, 3, 4, and I'm saying which. So my graph will remember which points are allowed to collide, which points are not allowed to collide. So let me replace the definition. I put here const gamma. Now, if I have an edge ij inside E of gamma, inside edges, which is edge in gamma, then xi should not be equal to xj. Yeah.
So, what about when you say right module, you mean with respect to the composition product and symmetric sequence?
Yes. Resolve everything. So it's associative. No, as you
Okay. I didn't get the point.
as you.
I mean, it's not an algebra already operate. It's a module.
It's a module.
Sequence.
So the thing is that so the algebra over opera is a left module.
Yeah.
So
there's a sort of else.
this is
a module over
so you have the collection of conf n
the one of the argument.
conf m times ed of m to conf
Explains so much.
d of n plus m minus 1. And this is associative, meaning that if you multiply it by ed of something, so then you can put brackets either here or here, right? And the algebra over it's you substitute something in the balls, and you have to substitute it in each place. So the key difference between right modules and the left module, that the right modules is an abelian category and the left modules are not. So you have, if you walk
one argument and not linear.
yeah, one is linear, another one is not.
The composition of functions.
Yeah, precisely. But still, let me say one more word, so that still using this notion, using this structure of the model over the little disk operator, you can say quite a lot about the configuration spaces. And nowadays, people were able to prove, for example, the following statement. So if you want to say what is the rational gamma p type of the configuration space, on which it depends. So what is known is that it depends on the, of course, it should depend on the rational gamma p type of X. Also, it should depend on the rational gamma p type of this little disk operator, of this data coming from that story. And the statement is that that's it. But what people know that, so it's known. So that rational homotopy, new homotopy type of conc n of x depends on new type of x itself. Now it's known when dimension of n greater equal than 4. Dimension, sorry, so d is greater equal than 4, or n is also some bounds on n, and also for instead of q, it's better to say it with r. So the notion that this story depends on q is known only in some bounds. So for d, n, and I don't remember precisely the given bounds, and the best proofs of this statement uses this theory of the right model over the little disk operator, because now we know quite a lot about the rational gamma p type of this operator, and this is quite a lot of story behind all this thing. Yeah.
The standard contract is just for the complete graph,
Yeah.
and the discrete graph corresponds to product. Okay.
Yes. This is what I would mention. So now coming back to this definition. So this definition, so I want to introduce, so instead of considering arbitrary points, so I'm allowed to collide some of the points. So the rules for those points who are not able to collide are given by the graph. So precisely the standard conf n of x is precisely a conf that corresponds to the complete graph. And also if you have the disjoint union, if your graph is disconnected, then it's the product, the corresponding configuration spaces do not know anything about each other. So this is the product gamma 1 of x times conf gamma 2 of x.
So for these guys, there is no symmetrical patch.
But there's the action of the automorphism of the graph. So you can remember the vertices. So there is some symmetry is behind the story, but of course not the full as it is for the symmetry. Then what the claim? So so this is the first restriction. Second, so what I want to say, so you will replace n with the simple connected graph. But simple means that there's no loops, no double edges, because what I have to know, so first of all, that the points may coincide with itself, so there's no reason to have any loop. And second, the double edge is the same story as one edge, because you only have to know if these points collide or not. So it's no reason to have many edges between different points. Okay, so this is nice. So but now that's the next question is what happens if I increase 1 point by instead of considering just small points, I want to consider the small balls, and I want to input one ball inside another. And I want to say that I can do absolutely the same story with the same rule, saying that yeah, I already erased this story. So here ij inside gamma. So I consider in the balls, and I do not allow balls intersect with each other whenever there is an edge in my graph. So for example, I can enlarge, I can consider 1, 2, 3, 4. So this picture is allowed for the graph 1, 2, 3, 4. So where 1 and 3, there is no edge between 1 and 3, so therefore I allow these balls to be intersected. But the 1 and 2 and 1 and 4 are not allowed to be intersected because they are connected by a graph. And I can embed this story inside one inside another. And now the question was what should be replaced here. So you see here before I have ed of n to ed of n plus 1. So now here I want to have gamma. It depends on what graph. So then inside 1 point I want to substitute also G, where G is a subset. This is the subgraph, full subgraph on a given subset of vertices. And what will be here? So when I draw this picture, so then when I have points here, so I have some graph here, I have some graph on top of it. All right, so the statement is that I want to, the result will be a contraction of one graph inside another one. So this is precisely, so this picture will be here. I have gamma. Here I have gamma restricted on the subgraph G on the subset of vertices, and here gamma with the subset of vertices contracted. And this is why this is called contractad. So this is contraction plus the opera theory. So you have the same kind of operations as you have for the operas, but you increase the number of objects that index your set of operations. So you increase, so you are dealing with, instead of working with just the numbers, you are working with the graphs, with the simple connected graphs, with this kind of operations. And so this contractad that in C is the collection of P from gamma to objects of C, and then for each subgraph in a graph, so you have gamma restricted on G, so gamma mod G, gamma restricted on G, and the map to
From the collection of all graphs, right? Not from.
yeah. For each graph you have P of gamma.
Is that just notation for the
Yeah,
category
this
of
is
graph?
this is the notation for it. Story. Okay, so now, and of course, absolutely the same is true that the configuration space you have is the right module over this contractad as you want. And now, so this is the key. So if you learned this definition from my talk, I will be happy. And now what I want to do, I want to give some advertisement about some results which we have about precisely this little disk contractad. There are some other contractad and some interesting examples of contractad, which maybe if I will have some time I will say, but I think I will have this opportunity, but so. So let me say some advertisement of the results. Of known results for little disks. Contractad. So I will do it together with the comparison what is known for the little disk operator. So here will be operadics, operad, ED, and here will be contractad. So the first story is the simplest case is d equals 1. So for d equals 1, when your manifold is just a line, so you consider RD, so you consider configuration of points on the line. This is also the starting point for the whole operad theory. This E1 operad is, so what we know about E1. So the first of all, the homology of E1 is the so-called associative operad. Because this sorts of n consists of what? So you have configuration of points on the line. So you have x1. So the only thing you have to know is what is the order, how they placed on the line. So you have x sigma of 1, x1, x2, blah 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 xn, but they may be placed in different orders. So you can do maybe x2, x1, and so on. And for those who are familiar with the notion of the left module over the operad, so the algebras over this operad are precisely the associative algebra. So the associative of n is just the k of Sn, so it's indexed by the permutations. Now what we have on this side, on the contractad side. So for the contractad side, so if I have graph gamma, once again, I have points on the line. 2, 4. So some points may coincide, some may not. But for those who may not coincide, for example, here it was 1, 2, 3, 4. So 1 and 3 I can interchange. But 1 and 2.
Fixing the collection of
Yeah.
all corresponding graphs before you starting a concrete control.
Sorry?
I mean, what is a concrete contract? What is contractad ED? You mean for each
D.
graph, to each graph you assign something?
Yes.
Okay.
The collection of disks such that they do not intersect when they are when the points are not connected by an edge.
To each graph you assign to each finite graph. Okay.
To each finite graph, I assign the generalized configuration space on RD.
Yeah, yeah.
So then topologically, instead of point, I'm considering the
Yeah,
disk,
yeah.
or there is another model which I will say a couple of minutes ago about further about the
So the arity is the graph.
yeah, the arity now in the graph. Yes, precisely. So for each graph, you should assign this E1 of gamma. So now E1 of gamma, what I want to say, it's also same as here. So this is the union of contractible spaces, union of subspaces in, so it's you have R to the number of vertices D of gamma, you take all this xi equals 6j for ij and h in your number. So what does it mean? You have to, so you have the RD and you take off the half spaces. So the all this the topology of the space is just the union of convex subsets. So the only thing you have to know is the number of how to recognize how many connected components you have. And in order to recognize what is the connected component is, so you have to say whether xi is greater than xj or xj is greater than xi. So what does that mean? That it means that on the graph you have to say, you have to place the orders saying that which point is greater. And of course the cycles may not appear because then x1 is greater than x2, greater than x3, greater than x1, which is forbidden. So this is, so the set, this H of E1 of gamma consists of acyclic orientations of gamma. So the only thing you have to know is just that you have to place, making it in a pole set, saying that which element is greater than which one. So this was the first story. The second thing is the not only for d equals 1, quite important story is not only the homology of E1, but there is also the so-called FM1 of Fulton-McPherson compactification, which tells me, so this is, as always in this theory of configuration spaces, instead of replacing the points by disks, you can remember, you can keep the points as points, but you can remember how points are collide to each other. So you allow them to collide and you add this as a compactification. You add this graph. So I don't want to go into the details of this Fulton-McPherson story, but this is another way to saying this story. So this description is not a closed set, and Fulton-McPherson is really a compact set, but with boundaries, which is quite nice for some applications. But maybe the first application is the name for this FM1, because FM1 is also known as Stashev polytope. Because this is Stashev polytopes for n equals 1, so you precisely remember how points are collide to each other. So this is Stashev polytope corresponds to the one connected component when 1 is less than 2, blah blah blah. So I'm claiming that on this side you have the same story. Yeah. This is associahedron. Yeah. Also hydra. So on this side there is a notion of P associahedron. Which is, so I found it in the literature, so this is Newton 21st, person whose name is Galatian. But the key point is just to so the story is that, so it's not too complicated to define it if you, whenever you have this kind of definition. So when you try to look on Fulton-McPherson story here, then this notion comes out immediately, but still you get quite nice examples of the associahedrons, which I also find quite interesting. So the next step, the next story, oops, so this, yeah, the d equals 2 story, or maybe 5 minutes that I will try to. So d equals 2 is that the homology of P2 as an operand is known as a Gerstenhaber operand. And what we know about this Gerstenhaber operand, that this is a quadratic Azul Yeah. Generated by binary relations, binary generators. So that means that the generators in this story are just given by E2 of 2. So 2 is the 2 points. But what is nice that on this side, you also have so E2, so for the I do not have so many simple connected graphs on 2 vertices. There's only one, which is given here. So these generators are the same generators as here. So you can so this is you have the same story here. So the corresponding operand is also a quadratic causal generated by binary quadratic relations by the same generators, but you have extra plus extra quadratic relations, because for the quadratic relations is the relations for, so these are generators and relations are in E2 of 3. So when you have 3 points, but for 3 points I have 2 graphs, 2 simple connected graphs. So one of them is a complete one and another one is this one. So for this one you have to add this kind of relations to this story, and then the claim is that you still get everything. So you can define the story with this ED of gamma with the contractad. So it's not too complicated to say what is the contractad given by generators and relations, and what is the notion of the being quadratic, being causal, and all this machinery which we know for the operand theory can be generalized to the notion of operads. And this is quite nice example because you can say quite a lot out of knowledge for 2 graphs. So then, and this is of course this notions it doesn't really depend on 2. It's known for this story. It's true for all the way to the term. But the next story is specific for the dimension 2. So what else do we know? So the cohomology of E2, which is a cooperand. So we know also quite a lot about this cooperand. So this is the cooperand because the cohomology have the multiplicative structure. So you have the notion of the multiplication on the on these spaces, on the homology, on the cohomology of these spaces. The only thing is that cohomology is contrary factor, so you have to switch the arrow in that story. Now this contractad and this ED of E2 of N is the so-called Orlik-Solomon algebra. And so you generated by omega ij. Omega ij is the J, so you have very nice representative for the homology. I'm using the story that R2 is equal to C. So this is the key point, key observation, which is so Z is a complex variable here. And the relations are omega j, which omega A plus omega K, I equal to 0, so-called Arnold relations. So what is nice that this is the quadratic, also quadratic causal algebra. And you also the operand structure is also very simply given because you have to say where these forms are going. So this is this the mode of E2 of N times of M and this one. So this should be the map of algebra. So you only have to say where omega ij is mapped, and they are mapped to either omega ij times 1 or 1 times omega ij, depending on whether these points ij are, so either they here or they are connecting this one with that one. So more or less the same story happens on this side, on the contractad level, but once again, so you have to, so the difference is here. So you have the cohomology of E2 of gamma is equal to this OS gamma, which is algebra generated by this omega ij, where ij is an edge in my graph, but the relations are given by the cycle. So here the relations was given by, you have ijk, so you have a cycle between ijk, and you forget one of the edges in this cycle. So here the relations will be looking for the minimal cycles in your graph, and also take away one of those edges. So these relations may not be quadratic. So for what this is a problem? This is a problem for me because this is the homotopy day. So now I'm coming to the homotopy story. And so what is known for E2, that also E2 of n is the K EB1 is a KP1 space. So this is given by the which is the, this is pure braid group. So on this level, on that side level, so this is because of this existence of non-quadratic relations, there will be high MSA products practically. So this will be, so this is E2 of gamma is E1 only if gamma is chordal. Well. So the chordal means precisely that any minimal cycle is, yeah, so there's a chord in any cycle. So all minimal cycles are triangles. So that means that this is precisely equivalent to the story that the relations are quadratic. So in this case, you will have this, the same story that this will be K1. Otherwise, this is some more tricky space. And moreover, yeah, so time. So then, then the last thing that which I want to mention is the rational. So what is important for me that the finding the rational homotopy type for E2 of gamma is still open question for me, so I don't know the general answer. I know the answer on this side, which is given by Conrad-Rinfridli algebra, so that we really know quite a lot about this modes of completion on that side. And maybe the last thing is that you can, however, you can write down the generating series. Generating series for both for the left hand side and for the right hand side, but maybe, yeah, maybe I have to stop here. Even they are quite interesting. No, maybe so here. So let me say that here, this is the chromatic polynomial. Polynomial of gamma. Here, if you try to compute it, and on the left hand side is also something quite known, so the chromatic complete graph, which you are able to write by yourself. And you can write down the bigger generating series on top of them. And the last thing is that for D would be D greater than 2. The question that really bothers me is that I don't know if the contractad is formal. For conjecture, the contractad indeed is formal. So formal means that the chains are the same chains are homotopy equivalent to the homology. What is quite known for the little disc operator, and which is quite useful for this configuration spaces. This is not true for the frame configuration spaces. And this is why this really bothers the story with the configurations on the non-polarizable spaces. But even for the, when you go to this generalization, so we were able to prove this formality only for d equals 2 and d equals 1.
Everything is in characteristic 0, right?
Definitely, yeah. Okay, so sorry.
I think we have time for one question.
Sorry.
Did you consider the generalization where you